Solving ideal transformer problems looks complicated until somebody explains it properly.
Hey everyone, welcome back to The Explainer. Today we're tackling the math and the physical logic behind ideal transformers. If you're gearing up for your CSEC physics exams, you probably already know that electromagnetism questions can be a bit of a roadblock. But don't worry, our goal today is to totally break down the relationship between turns, voltage, and current so you can walk into that exam room ready to bag full marks on literally any transformer calculation they throw your way. Okay, here's our game plan for today. We'll be looking at the ideal assumption, step up versus step down, the inverse twist, the hero calculation, and finally, dodging exam pitfalls. Let's jump in. All right, part one, the ideal assumption, setting the baseline. Before we get into the nitty-gritty rules, take a look at this actual high-difficulty CSEC multiple-choice question. It says, an ideal transformer has a primary to secondary turns ratio of 1 to 3. An alternating potential difference of 200 volts is applied to the primary coil, and a resistance of 200 ohms is attached to the secondary coil. What is the current in the secondary circuit? Now, don't sweat trying to solve this right now, okay? Just stick these numbers in your back pocket. We're going to come back and absolutely demolish this question in a bit. So to crack a problem like that, we really have to zero in on one single word, ideal. In physics land, an ideal transformer is this theoretical magic box operating at 100% efficiency. Practically speaking, it means the electrical power going into the primary coil is exactly the same as the electrical power coming out of the secondary coil. Literally, zero energy is lost to heat or humming sounds. So when a CSEC problem explicitly drops the word ideal, it's basically handing you a massive physics cheat code. Power in equals power out. That single fact right there is what makes all the math we're about to do possible. Moving right along to part two, step up versus step down, the common sense check. Listen, before your fingers even touch that calculator during the exam, you need to ask yourself one incredibly simple question. Did the voltage go up or did it go down? Examiners specifically design these questions to see if you're actually using your physical logic, not just blindly crunching numbers. If you intuitively know how a transformer is supposed to act, you'll spot a calculator typo from a mile away. Let's break down the two flavors you're going to see. First up, the step-up transformer. The defining feature here is having more turns on the secondary coil than the primary coil, so NS is greater than NP. Because of that, your secondary voltage, Vs, shoots up higher than your primary voltage, like a 1 to 3 ratio, right? The voltage literally triples. On the flip side, we've got the step-down transformer. Here, the primary coil is the one with more turns. NP is greater than NS. And what happens? The secondary voltage drops. Vp is higher than Vs. You might see a ratio like 3 to 1 here. Step-down transformers are everywhere in everyday life. Like when you need to step down a massive 120-volt wall supply to a super safe 18 volts just to charge your laptop. Recognizing this direct, proportional link between turns and voltage, that is absolutely your first line of defense. Which brings us to part three, the inverse twist, currents balancing act. Remember that cheat code we just talked about, power in equals power out? Well, bringing it back to the syllabus, we also know electrical power, P, equals current, I, times voltage, V. Because our ideal transformer absolutely has to keep power perfectly constant, it sets up this really cool balancing act. I mean, if the voltage spikes in the secondary coil, something else has got to give to keep the total power completely flat compared to the primary, right? That something is the current. It is mathematically forced to adapt. And wow, here is the twist that trips up so many students. Check out the standard ideal transformer formula. On the left, the proportional voltage ratio. Notice how perfectly aligned the secondary variables are on the top. Vs over Vp equals Ns over Np. Turns go up, voltage goes up. They move together. But wait, look at the flipped current ratio on the right. Ns over Np equals Ip over Is. Notice that? The primary current is on top. The whole relationship is completely flipped upside down. It's inversely proportional. If a step-up transformer cranks at the voltage, the secondary current must shrink compared to the primary to keep that power perfectly balanced, and vice versa. If a step-down transformer slashes the voltage, the secondary current actually has to go up. All right, part four, the hero calculation, bringing it all together. Okay, let's grab those numbers from earlier. We had a turns ratio of 1 to 3, a primary voltage of 200 volts, and a secondary resistor of 200 ohms. They wanted this secondary current. Here's your bulletproof roadmap for these problems. Step 1. Look at the 1 to 3 turns ratio. That second number is bigger, so boom, common sense check, it's a step-up transformer. The secondary coil has 3 times the turns, which means the voltage has to triple. We use the turns ratio to find the secondary voltage. 200 volts times 3 gives us a secondary voltage, Vs, of 600 volts. But hold on, we are not done. The question asked for current, and it handed us a resistance. That's your cue for step 2. Once you have that secondary voltage, the secondary circuit is basically just a normal DC circuit, so you dive right into Ohm's law. Current equals voltage divided by resistance. That gives us our new 600 volts divided by that 200 ohm resistor. And if we execute those 2 steps perfectly, we get our final answer, 3.00 amps. Going back to that original multiple choice list, option D was 3.08. By just staying organized, finding the voltage first, and then hitting it with Ohm's law, we literally coasted to the right answer without getting tangled up in the math. Finally, part 5, dodging exam pitfalls, keeping your marks. Okay, before you run off feeling like a transformer wizard, let's talk survival. Exam reports show exactly where students leave easy marks on the table. First up, mixing up primary and secondary labels. People are constantly jamming primary values into the secondary side of the equation. To stop this cold, literally, write down and label your data, VP, VS, NP, NS, before you even touch a formula. Second trap, forgetting the Ohm's law step. We just saw this, right? People calculate that secondary voltage, feel super proud of themselves, and just stop. If they ask for current and give you resistance, you absolutely have to do part 2. Third, ignoring the step-up or step-down logic check. If you calculate, say, 50 volts on the secondary side of the step-up transformer that started at 100 volts, well, you flipped the ratio. Always pause and think. Fourth, omitting SI units. This is huge. You will bleed partial credit if you just write down the number 3. It's got to be 3 volts, 3 ohms, or 3 amps. Slap a V, an omega symbol, or an A on every single final answer. And lastly, failing to show substitution steps. Examiners want to see the formula, the substituted values, and the final answer. Never just plop down a final number, even if the math was incredibly easy in your head. Look, to keep all your hard-earned credit, sear this one core principle into your brain for every single calculation. Always remember that if voltage goes up, current must go down. That let be your North Star for electromagnetism. If you run a calculation and both your voltage and current went up, stop right there. You've definitely misapplied the formula. All right, since we've completely dismantled the math and logic of the flawless ideal transformer in this explainer, I want to leave you with a real-world puzzle. If the ideal assumption perfectly balances the math on paper, what physical forces out there in the messy real world prevent that actual transformer sitting on the power pole down your street from ever hitting 100% efficiency? Seriously, where does that missing power actually go? Definitely chew on that as you dive deeper into your physics studies. Thanks so much for joining me on this explainer, and hey, good luck crushing those calculations.
As always, the link for this study tool is in the description below. Let me know what you think in the comments.